Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about lead acid battery, the granddaddy of all batteries. So let's dive right into it. Well, there is a very tangible reason why I'm classifying lead acid battery as granddaddy, simply because it's been made in 1859. Yes, you heard that correctly. It's 1859, not 1959. So it's an ancient technology. It was made by Ganson Palte. Again, the name is in different language, so sorry about wrong pronunciation. And it's more or less 161 years old. Let that sink in. This technology is 161 years old. Now, many people don't like lead acid battery because it has one critical flaw. It does not have very high energy density. Basically, the amount of charge you can put into this is not much. However, even that being true, it still has one of the YOLO performance, which we call high power density. Basically, it does not have too much power. It does not have like, okay, I can run your home for like, a few days. It has enough power that even if you dump like only few kilowatts into it, it can dump all of that almost at the same rate as a capacitor. So it has ludicrously high power density. That's why a lead acid battery can start your car. But if you try to do that with a lithium ion, you're gonna set lithium ion on fire, because very few lithium ion chemistry can even come close to handling the power output that this puppy can do. And to give you another context of that, it's first rechargeable cell. Now there are two types of cell: primary cell, basically use and throw, which you use in remote controls and watches and all that jazz, and then you have a rechargeable cell. Now this was made so early that at this point in time they did not even have generators, so they had to make primary cells just to charge this and to figure it out. So let that sink in. This technology is tangibly old, ancient, and time tested. It became the foundation of electric cars basically, and cars became a reality because of this. After this, then petrol engine came and internal combustion engine became refined enough, powerful enough that they got displaced. So let that sink in. This is a thoroughly advanced technology. Now, how the heck this technology work? It has three core components. Now, you may say more or less that's the same amount of components used in every other chemistry. But yes, many times you will say lithium-ion batteries does not mean just lithium. It means hundreds of other things. And many times companies go to extreme length to add some special sauce, special mixture, special alloys to improve the efficiency. Here, it's inherently simple. Inherently, all you need is water, preferably diluted I'm saying, preferably absolutely pure as you can distilled water. You need lead, high quality, better, and you need sulfur, high quality, better. That's it. It requires three components. So what does this mean? That simply means if you want to make a factory in Nepal, you can do that. If you want to make a factory in India, you can do that. It does not have that monopoly issue. Basically, water, lead, and sulfur, they are very easily available in almost everywhere on the planet. Everywhere in the planet, you may not have like okay, abundant supply of sulfur, but you will have more than enough. Like, that's not an issue. So sulfur in this equation is the carrier. The reason why we say is a lead acid battery is simply because lead is the primary electrodes. Anode and cathode is made out of lead. Then the charge carrier is from sulfur. Now sulfur plus water equals acid. That's why we call lead acid battery. Now in charge state, when you are like, okay, battery is charged, fully charged, ready to go, so what happens in that state, in charge state? The liquid inside, generally water, has a maximum concentration of sulfur oxide. So what does that mean? That simply means this is acidic, very acidic. And you have lead or raw lead on one side. Generally people do not make it 100% pure lead, simply because 100% pure lead is not very strong. So, and if you have charge ions going through it back and forth, and that also causes temperature increase on a molecular level, it expands and contracts, it will shatter. So generally they alloy it with something or have it into a mesh where it can hold its shape. So you will have lead, try to get it as pure as possible. Then you have lead oxide on the other end. This creates the potential difference that allows for charge flow. So this is your charge state. You connected a load, you started discharging, your battery is completely discharged. What happened then? What happened is basically sulfur oxide went away from the water and directly went into the electrodes. Anode and cathode both turned into lead sulfate, basically PbSO4. That's what happened. Sulfur literally evacuated from the fluid and went into anodes and cathode. Now when you charge it, same thing happens, only in what? You basically push out sulfur. It's like, bro, don't stay in the anode or cathode, go into the liquid. That's all there is to it. Sulfur is going in and out, in and out. It's inherently simple, it's inherently reliable. The reason why these cells do not last forever is simply because, again, on a molecular level, you see the lead is getting destroyed. Basically every time you are charging it and discharging it, you are basically forcing sulfur in, pulling them out, forcing it in, pulling it out. That causes inherent limitation, including high temperature output, and the side effect that the way you are doing this is inherently electrolysis. Basically, you have water here, you are putting electricity there, you made a electrolysis cell, you are making hydrogen leave the system, and that's why lead acid battery also have a tendency to go boom. Now they do not do anymore because A, we are very good with it, we had 100 years of experience to handle it, and B, the flow hydrogen outflow is not too much, and the sulfur also does not have the reaction, primary reaction itself is not it's just mass producing sulfur. So otherwise, like, these batteries will be turned into something where it's like, yeah, just have tanks of water into your car, but otherwise the battery will not work. So hydrogen outgassing is there, it's a serious threat, it does happen, it does set things on fire, but it's very well managed, and unless you are ludicrously stupid or ludicrously careless, it will never happen. So that's how the working happens. It's basically your sulfur is going from liquid to your anode or cathode, and back to liquid. That's all there is, charging and discharging. Sulfur is the main carrier. I have provided a very detailed documentary where you can follow the ion path and figure out how each ion is behaving into equation, and that documentary is from US Army, and it's surprisingly old but surprisingly good. So I would urge you to watch that for if you really want to nail down the chemistry. But that was the basic idea of the chemistry level. Let's understand the construction. Now construction, you have to understand this. Every chemistry has an inherent potential value, aka the voltage. Potential value as in potential difference. So if you make a lithium ion battery, you're like, let's say a lithium ion cell, you're like, okay, I'm getting 3.2 volt. Will you get the same 3.2 volt if you make it huge? Answer is yes. Will you get the same amount of voltage if you made it ludicrously small? Yes, that's right. Even your watch lithium ion will also have 3 volts. So that's the reality. Cell voltage never changes depending on the size. Ampere does change, amp hour changes, but never the voltage. Voltage is inherent to the chemistry. That's why lead acid also has an inherent voltage of 2 volts. So each cell in a battery, it's 2 volt. So when you completely discharge it, in optimum scenario, you should only discharge it to a point where it's each volt cell is reading 1.8 volt. That's discharged it. And when you full charge it, each cell should read 2.1 volt. Multiply these by 6 to get a rough idea what your charge and discharge curve should look like. And for more precise information, just go into the website of the battery manufacturer. They will have like complete charge curve and all that. And it's surprisingly stable. It's like surprisingly most of the thing happens around 13 to 12 volts. But again, depending on deep cycle batteries, you can go very low as 10 volts. So we generally 2 volts is not that useful, so we generally couple 6 of them and make a 12 volt unit. Now 12 volt is standardized, so that's why you will never get a 24 volt battery. You will always get 12 volt battery. You can connect multiple of them, but you will always get a 12 volt battery as a standard. However, there are in certain scenarios where you need really long life, long lived battery packs. There you will get single cell as a unit. So you will buy how many volts you need. You will buy cells directly according to that. So if you need some awkward voltage where it's like instead of 48 volt you need exactly 40 volt, you can reduce 2 cells. You can buy each 6, and these have ludicrously long lifespan. And in case you damage one of them, you can replace that cell rather than throwing away the whole battery. So this is how it works. Now plate geometry, you will always hear this word plate with lead acid battery, and sometimes you type plate batteries, the first thing you will get is lead acid battery. Is that plate geometry is directly proportional to charge flow. Basically, if your plate is very flat, allows a lot of charge to go in and out, it will become very powerful. But if you made your plate very thick, very reliable, very long lasting, it will not have the ability to let the charge go in and out very quickly. Side effect, your battery will be long lasting, but it will not have the oomph, the hundreds of ampere dumping capability that it would have had if it was thin. Some scenarios you will figure it out like, hey, do I need this or do I need that? So everything in a lead acid battery is directly proportional to the geometry. So it's no longer like, oh, if I have this chemistry, if I add this to lithium, like lithium titanate battery or lithium iron phosphate battery, it does not have something that complicated. It's very simple. The geometry is king here. You make the geometry better, you get an awesome output. You do not make a good geometry, you did. So that's why modern systems employ what we call tubular cell structures. Like there is literally tubes. Again, tubes are more like a casing that makes sure that when lead oxide degrades, again the material itself degrades every time you are charging and discharging, it does not just fall apart. So construction is directly we are talking about physical construction. It's much more forgiving. That's why even backwater country, you can easily see people who actually build lead acid battery. You can build it. It's quite doable. However, you should be careful with lead, basically lead exposure and all that jazz. It can be done. So what types of battery we make? Generally, there are two major types. Basically, one of them is surface charge. These are what we call automatic battery. Now, these batteries are small, but they are designed with one core component. Dump as much power as you can go as quickly as you can do. So these puppies, even they are small, like this, literally they are this big, they can dump 400 amps. Let that sink in. 400 amp multiply by that 12. See how much spike it can. And that's the sole reason why we still use lead acid battery in our cars. Basically, if you try that with any other chemistry than lithium titanate, you will set things on fire. Or you, to achieve that kind of power ampli, you have to have a huge battery. So that is why, like, a lead acid battery is very close to a capacitor. That's why it can do what we call cold cranking. Basically, everything is cold. You just turn your key, your car is like, I got this, bro. It turns like dumps like 400 amps. And in cases of trucks and all that jazz, it can go as high as like 1800 amps. Again, they generally use two batteries, and those batteries are huge, but relatively speaking, they're still much more efficient than any other mechanism. That's why these are still there. Like, everywhere you can still find this. That's the one primary reason. The ability to dump charge, it's like, is the king. Then you have another aspect, because they make plates very thin as they can make it. Consequence of that is that if you discharge them, you will physically destroy the plate. That's why if you ever had a scenario where, like, hey, the headlight was turned on for the like whole night, next day your battery is dead. Like, it's not that you can charge it and it will come back to, no, it's dead, simply because discharge and charging physically damages the cell. The whole reason why we still use this, simply because your car runs on alternator, not on battery. So batteries most of the time is like, hey, I'm gonna apply the charge, and then alternator is gonna keep recharging me. That's it. So that is why these are not designed for what we call deep discharge. It cannot handle deep discharge. So again, if you want to build solar home, or you want to build, like, the biggest battery bank, if I'm remembering correctly, 13 megawatt of lead acid battery. That's the biggest battery bank anywhere. If you want to make something like that, you need the ability to deep discharge. You need the ability to count on your batteries. Like, dude, you're gonna be there, you're gonna need you'll be there. In those scenarios, people will generally buy cell pack like this, basically, where you will order how many cells you need. And benefit is, like, yeah, you can replace it if anything faulty happens. Sometimes you will have transparent casing, so you can actually see if plate has been shorted or damaged or not. And these have much thicker plate. That's the whole point. I specify the geometry is king here. It's not like, advanced chemistry and a hoo-ha. No, it's just geometry. You can see it and tell it, okay, what the hell that means. So I have a 220 amp hour battery bank in my main home. That's, again, it is very heavy. Like, it was ludicrously heavy, but it does have power. And what does that power mean for us? That means, in case of my UPS, whenever the power goes off, and if I have too many components running at the same time, it can handle that spike. It's like, okay, I got this. And if I turn on things, specifically motors have ludicrously high spike demands. Batteries are like, I got this, bro, I got this. So that is why, if I wanted to do this with lithium ion, can we do that? Absolutely. It's just, you'll have to buy hundreds more. So inherently, these are the two main types. So you will find always people say, like, marine batteries are generally between surface charge automotive battery and deep discharge battery. Deep discharge battery, like huge ones, they are generally good for, well, actually running your things. And then you have car batteries. Many times you will see car battery ratings look so much more awesome. It's like, this has 60 amp hour capacity versus 60 amp hour in a tubular battery would be much more expensive. Reason for that is those 60 amp hour you can actually extract. You try to extract 60 amp hour on a 60 amp hour battery in a car battery, yeah, that battery is dead. So that's the difference. They are only designed for cold guys, like, they're fancy capacitors. Now, what we can expect in the future. Now, this is one thing that you have to inherently understand. When we say battery technology, it does not progress the way people think. It's like, oh, in the lab we saw something today, so next day it's gonna come into reality. Not even next day. It's not gonna come in 10 years. It may take as high as 50 whole years before it actually something comes out of it. Now, again, thankfully, modern industry is moving much faster, but still takes time. Anything that you are seeing nowadays, like, let's say, for example, graphene infused lithium ion batteries, again, they have been in development for at least 15 years, and at least 8 years ago, it was like, yeah, we actually see some potential in this. Now they are coming into some experimental power banks where they're like, yeah, this, you can charge this puppy very quickly. So that's the inherent benefit of lead acid. It's every aspect of it is thoroughly mapped out. Heck, we run submarine on this puppy. That's how reliable this thing is. So it's a very mature technology. Then we come to the another aspect. It's very forgiving and very tolerant. If you mess up lithium ion battery in terms of voltage, in terms of ampere, in terms of overcurrent, in terms of undercurrent, it's gonna burn your house down. Lead acid, it inherently can do that, but it generally does not, simply because a hydrogen leak off. While it's true, it does not leak off, like, you put 100 liters of water and it's just 100 liters of hydrogen you're gonna get out of. You only gonna get have small leak offs now. And not to mention, because we have been doing this for 100 years, we know this, and every vehicle that has a battery compartment, it will have a way of hydrogen to vent out. Every big building that's supposed to have large online UPS setups where they have like hundreds of batteries running into parallel, they will have a room with an exhaust system where it's like constantly running, so it does not have hydrogen pile off, does not happens. But it's very forgiving and tolerant. For example, this battery, this is generally what you have in your basically UPS. I destroyed my UPS to get this out. So it is a 12 volt 7.2 ampere hour setup. So it also has the same 6 cells unit. And if you read the cautions very carefully, it's like do not charge in gas tight container, because even if it is a sealed system, there is a leak that hydrogen will leak. And again, hydrogen leaks through almost anything. So they are like, dude, if you're overcharging this, please make sure you have hydrogen vent off so it does not cause a fiery explosion. And the probability you have actually heard or seen any places where they have actual damage of these batteries is very unlikely. And what happens if something punches through it? Nothing bad will happen. Like literally, that's the how secure these things are. You can literally have a train full of this and a train run through it, it will not catch on fire, nothing bad will happen. So that's the inherent benefit of that. Now, to give you a visual representation of size, this is 12 volt 7 amps. That's more or less around 82 watts, 82 watt hour capacity. That's the inherent capacity of this. This is a 20,000 milliamp hour USB battery bank. This has 72 watt hour capacity. This has 80. That's simple. This is what people say when it means like lead acid is 3 times bigger and heavier than lithium ion. That's what happens. However, if something bad happens to this, basically if it gets punctured, fire. If it gets over discharge, fire, damage, destruction. This, yeah, it does not give a damn. I can drop it right now, but again, that will clip the audio, so I'm not gonna do that. So that's the reality of this. This battery is very time tested and very forgiving. That forgiving aspect people generally ignore. Is like, hey, why don't we use lithium ion? We can use lithium ion, but we do not have 150 years of experience with that. So we do not know, okay, in this scenario, this happens. We do not know that. Lithium lead acid, we know everything about it. Like every conceivable, feasible thing we know about it. We have been doing it for so long. And another advantage, you may be like, okay, lead is very good and all, but it's very toxic. Again, lead is very dangerous for human body. We used to put lead directly into gasoline. That was a bad idea. We stopped doing that. So what about these batteries? Thankfully, lead is surprisingly easy to recycle. At this point in time, almost every country, which includes India, China, and every other major country with major population, we know how to recycle these batteries. And lead inherently is very recyclable. What does that mean? That simply means in around US has a public report of that. It's like batteries that are made in 2008 to 2012. Like they tracked all of those batteries from every manufacturer sold in USA. They achieved 99% recycling efficiency. Let that sink in. It's like every battery sold, they knew how it was recycled. So that's the whole point. Lead acid battery is super easily recyclable. So it's not something like, oh, I'm gonna contaminate the water. Like we got this. We can just keep recycling it however long we want it. And in terms of lifetime, people say no, lead acid does not last very long. That's true, but simply because business decision. It's like it's not a limitation of the engineering. It's limitation of companies. Companies, when they find a new design, let's say tubular design, they're like, okay, this tubular design will increase the lifespan. What they will do is basically they make the components as cheap as they can, so they have the same lifespan as the older batteries, but they're gonna sell you for a higher profit. Basically, they will keep the price same, but because they reduce the component cost, they're making more profit. So that's why. And if you really can afford it, let's say the batteries that goes into submarines, those last very long time. Like you can buy Exide batteries which have like a warranty of 25 years. That's simple. 25-year long warranty. Again, the plates are huge and thick. Density wise, don't even think about density, nor in terms of power, simply because to get that power oomph, you need thin plates. Thin plates do not last. So if you want to build, let's say, power backup for a server or large data banks, generally people employ lead acid battery with online UPS system. And some systems are as high voltage as like 3000 volts. Again, lead acid is time tested. We know how it works, and again, they know what they are doing. And many scenarios they have like liquid filling system, so everything they can test. And this is another aspect of it, because the basically concentration of sulfur into your water mixture, you can easily tell what is the state of charge. You won't have to make a guess based on voltage. You can know exactly what the charge is. So easily recyclable, very time testing, very forgiving, and very long life. When you actually invest a lot of money into this, basically be it submarine or be it large data centers, it's still gonna be here. Like can we replace it with lithium ion? No. Can we replace it with lithium titanate? Yes. Why don't we do that? Lithium titanate is 10 times more expensive. And not to mention, lithium titanate will be only lighter, it will be still bigger because lithium titanate is much lower density. So it is more or less end up in the same place. So do not expect in the future that all the lead acid is going to disappear. You don't have to worry about it, and it's not going to happen anytime soon. So this was our presentation on lead acid battery. It was a viewer request. I hope I was able to illuminate some of the topics regarding this, and this was helpful or funny to you. In those scenario, if that happened, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.